you later. Okay, let me quickly revise. That pressure exerted by one molecule is equal to force by area. Force we calculated last class, so pressure is equal to force by area. Are you following, Mazherul? Okay, so next time please be on time. Okay, so pressure is equal to force by area. Force is this much, area is L square, so mx square by L cube. This is by just one molecule. Now there are many number of molecules moving with different velocities. Let there be n number of molecules moving with ux1 velocity, ux2 velocity, up to uxn velocity. So when you consider all the velocities, you have to add the pressures by each of the molecule. So this formula becomes m by L cube into ux1 square. Instead of this ux square, you add all the velocities of n molecules. So ux1 square, second ux2 square, etc. up to uxn square. Now we have to simplify this much, where we get the help of VRMS. So what is VRMS? VRMS is say like this. Okay, VRMS. Yes, VRMS is equal to what? VRMS is equal to, what do we do to find the VRMS? V1 square plus V2 square plus V3 square up to Vn square. What do? We square all of them. Then we find the mean, root mean square. There are n number of molecules, so we divide by n. Then root means we find the square. This is the formula for VRMS. Okay. Now you can see that this part alone is similar to this part. So for that, first you have to get rid of this square root sign. How can we get rid of that? By squaring both, right? So we get V square RMS. V square RMS. How do we write that? V square is equal to what? The square root disappears. V1 square plus V2 square plus etc. Vn square divided by n. Now this one we need only this much. That means we need only this much. So what do? We cross multiply. So from that, V1 square plus V2 square etc. Vn square is equal to n into root, okay, n into V square. That means yes. Okay. So we are going to replace this one by n into V square. Okay. Mean square velocity. We did not take the square root. We find the mean square. So this has to be written in the place of this one. So this formula becomes P1 is equal to m by L cube into n into average of, instead of this V, our variable is ux square. Okay. Let me check. Yes. Understood, Fareen?
Yes, miss, understood.
So this is, say, equation 1. This is what? Pressure exerted by all molecules moving in x direction. So when they move in x direction, they hit this vertical wall. So that's why I put you P1. This is only one part of the total pressure. I'm not saying anything. I'm just writing so that to save the time. Did you finish up to this? When you're done, then you tell me.
Miss, can you pull the paper up?
Finished?
Yes, Miss.
Okay, so now you listen. So this, we considered only molecules moving in the x direction, hitting the opposite wall, exerting pressure. Similarly, particles are also moving in the y direction and they hit this wall. Particles also will move in the z direction and then they hit their corresponding wall. So there is also a pressure here, there is also pressure here. Okay, on all the three axes, there is pressure exerted. So we have to find the average pressure exerted by molecules traveling in all the directions. Okay, so that is our next step. So the average total pressure, we can say average or total pressure exerted by molecules moving in all the three axes, okay, is equal to, let the total pressure base say P, is equal to average. You have to find the average of all the pressure, and since they move randomly, all these pressures are taken to be almost uniform. So what is the average pressure you have to consider? So P is equal to, how will you find the average? There are three values. How will you find the average? P1 plus P2 plus P3 divided by 3. Okay, and okay, now you don't write. Okay, so now you have to write, since the molecules are moving randomly, okay, they are moving randomly with high speed, you can say that P1 is almost equal to P2, is almost equal to, say, P3. Okay, so what can we do? We have to find 1/3 of each pressure. Therefore, average pressure is equal to, P1 is equal to this much, 1/3 into 1/3 of this pressure, m by L cube. Okay, that means P plus P plus P divided by 3. You understood? Okay, so therefore pressure is equal to, you can write here, this average pressure is equal to P1 plus P1 plus P1 divided by 3. That is what I am writing over here. Okay, that is what I am writing over here. Did you understand why do we do like this? Since the molecules are moving randomly, all the pressures are assumed to be equal. Did I write that? The pressures are assumed to be almost equal. The pressure exerted on all the surfaces are almost equal. Therefore, this average pressure is equal to P1 plus P1 plus P1 divided by 3. So now when you put the values 1/3 into, what is our pressure P1 formula? M by L cube into N into U X square. right up to this. Why I'm dictating? Because this is an important derivation and a difficult to remember derivation. So all these steps should be done, and you have to write and learn so that this should be done within set 10 minutes maximum. You can take it for writing this derivation. Okay, all these explanations are not there in your textbook, so you may wonder how these steps came. That's why I'm making you write all these steps.
Miss done.
All of you done up to this? Okay. So now you have to make a general equation. This ux is a problem. Okay. To make a general equation, this ux square should be replaced by mean square velocity, which we write always by the letter C. Okay. To make a general equation, this ux square should be replaced with C square. This is the next modification that you are going to write. So you write in your copy, to make a general equation, be replaced with C square to denote the motion in all the three directions. Are you here up with me?
Yes, miss.
So average pressure is equal to 1 by 3 m n c square, okay, divided by L cube. Is this equation? Yes. Okay. So now here also we have to make a few substitution. Since m is the mass of one molecule and n is the number of molecules, what is m into n becomes total mass of the gas. All right. Now what is L cube?
Volume.
Okay, so you have to make these two substitutions here. So this equation becomes the average pressure is equal to 1 by 3 capital M C square by volume. This is one of the final equation, and this is called kinetic theory equation, because this is the equation derived using the concepts of or the assumptions of kinetic theory. This is the kinetic theory equation, or according to kinetic theory, pressure exerted by gas on the wall, average pressure is equal to 1 by 3 m by v c square, kinetic theory equation. Now also you know that m by v, what is m by v? Mass by volume. What is mass by volume?
Density.
Density rho. You can also make that substitution. That is easy for you to remember. Average pressure, okay, or we simply write like this: pressure is equal to 1 by 3 rho c square. Okay, very easy formula, rho c square. Then you can expand the rho, come back to this, and you can keep on expanding to reach the earlier steps. Okay. So this is a formula to find what? The pressure exerted by a gas on the walls of the container. Done. Now we continue this derivation to get an expression for temperature, and that derivation will tell you the temperature is a measure of the kinetic energy of the gases. So this is the derivation of expression for temperature. Okay, fine. Now you stop writing, I will explain. You remember the steps that I am doing, then you try to write it on your own soon after my explanation. Okay, so now try to memorize this one. Very easy if you follow me. Okay, now what is kinetic theory equation? According to kinetic theory equation, the pressure exerted by gas on the wall is 1/3 rho c square, which means P is equal to 1/3 m by v c square. Okay, so from this, what is PV? What is PV? PV is equal to 1/3 m c square. This is according to kinetic theory equation. All right. Now you have also learned another PV equation from the equation of state. Equation of state of ideal gas. For say n number of molecules. N number of molecules.
PV is equal to NKT.
Yes. So PV is equal to NKT. This is the equation of state. This is kinetic theory equation. Now this capital M can be replaced with what? PV is equal to 1/3 m is small m capital N into c square. Capital M is equal to small m into n. This is also equation 1 you can write. Now the LHS are equal, so these two are also equal. So from equation 1 and equation 2, what do you get? NKT is equal to 1/3 m n c square. Is this right?
Yes, miss.
Now cancelling n from both sides, what do you get? K into T. What is K? Sanjida? What is K? It's constant. That's why I write KB. I write KB. It's a special constant. What is this one?
Boltzmann's constant.
Boltzmann's constant. Okay, 1 point something. Boltzmann's constant is equal to 1/3 m c square. Now, see, look at this. What is 1/2 mv square?
Kinetic energy.
Kinetic energy EK. Okay, see, this is also similar to this. If you make this 1/3 as 1/2, then you can replace this one with kinetic energy. You got the idea? You're trying to compare. The only problem is that here you got 1/3, but you need 1/2. So what should you multiply this one with so that you get 1/2 here? You multiply with, you have to remove this 3 and you have to bring a 2. So you multiply both sides with 3/2. 3/2 KB into T becomes 1/3 into 3/2 MC square. Did you understand this step?
Yes, miss.
Okay, we are multiplying with 3/2. Now this one goes. See, you got half MC square, half MC square, half MV square. This is velocity, this is average velocity, that's all. Now what can you write? You can write half mc square is equal to 3 by 2 kT. Very, very important equation. So from this, what is temperature? T. We are trying to derive for temperature. What is temperature? This 2 and this 2 goes. Okay. This 2 and this 2 goes. Temperature is equal to mc square by 3 kb. This is the expression for temperature. But this is of not much use to you for your exam point of view, but this is important. But this tells you what? Okay, this tells you that temperature is an average of temperature. Now, this is a constant. You can write what is half mc square. You can write average kinetic energy. Okay, average kinetic energy is equal to 3 by 2 kb into T. Therefore, temperature is equal to, this is a constant, this is a constant directly proportional to average temperature. So this is how you define temperature. Temperature is, what is the definition that I told you to remember? Is a measure of average kinetic energy of all the molecules in an object. Okay, this is very, very important, very, very important. So this means that what, at a particular temperature, all molecules have same kinetic energy. Try to understand this concept. Many a times in multiple choice they get at a particular temperature, okay, all molecules of a gas has same average kinetic energy. At a particular temperature, all molecules have same average kinetic energy. But this has a problem. Assume that you have got hydrogen molecule, all hydrogen molecule. This is, I'd say, 200 Kelvin. Okay. Now all of them is at 200 Kelvin. So what can you say? All hydrogen molecules have same kinetic energy. Understood? All of them have same kinetic energy. Now you think this is another mixture of hydrogen with helium. Hydrogen and helium. This is also maintained at 200 Kelvin. Now what can you say? The kinetic energy of, okay, what can you say? The average kinetic energy of hydrogen and helium are same. Why? Because same temperature, at a temperature. How can that be possible? Hydrogen is small, helium is big. How can they have same kinetic energy? Hydrogen is small, helium is big. How can they have same kinetic energy? The kinetic energy explanation is what? Ek is equal to half mc square. This m is different. This is hydrogen, this is helium. Helium is big mass. How can they have same kinetic energy? This is where the difference is. Okay, so that means the kinetic energy of hydrogen should be equal to kinetic energy of helium. Okay, that means half m, say let's say the speed of hydrogen, a mass of hydrogen into c of hydrogen square. should be equal to half of mass of helium into C of helium square. They must be equal. But mass of hydrogen is smaller than mass of helium. So even this decreases, this has to increase. So that means mass of hydrogen by mass of helium should be equal to helium square by hydrogen square. C of helium by C of hydrogen square. So what does this mean? As the mass increases, mass of the particle increases, their average speed decreases. Very, very important concept. Did you understand this? So let me tell you this once more. At a particular temperature, a mixture of gas has same kinetic energy. But if that mixture is made up of different masses of molecules or molecules of different masses, bigger mass molecule will be traveling slow, small mass molecule will be traveling faster, so that their kinetic energies are equal. Is this understood?
Yes, miss.
Okay, so this derivation also take it down because very important. Okay, otherwise, yeah, just take it down. Derivation of temperature. Derivation of temperature. Please understand every step. So what is this actually? According to kinetic theory, we have learned that molecules are moving randomly with different velocities. Okay. Randomly in all directions with a variety of, with slightly differing velocities. Randomly with different velocities. Okay, now how different are their velocities? How different are their velocities, or how different are their speeds? That is what shown in this Maxwell distribution curve. This is at a particular temperature. At a particular temperature, even though we say that their kinetic energies are same, but it is not the individual kinetic energy, it is the average kinetic energy. That is why we take RMS velocity or RMS energy or average energy. Okay. Now, why should we take that average energy? That is explained by this one. Now, this Maxwell's distribution curve is like this. It can be either in terms of the kinetic energy or speed of the molecules, right? And in the y-axis, what do? We have the number of particles or molecules having this much speed, certain speed. Here what do you have? Number of molecules, again having certain kinetic energy. Okay, having certain kinetic energy. What does that mean? Assume that the speed here is 0, the speed here is 10, the speed here is 20, 30, 40. These are not the correct values, some random values. At a particular temperature, assume that you will have a graph like this. What does this mean? This means that there are this many molecules, this number. For example, this is 100. Okay, if this is 100, there are 100 molecules having speed 10. And say look here, 20. There are this many, maybe say 100, 200, 300. 300 molecules are there having speed 20. And there is a peak. So this is the peak. What does this peak? That means this is the maximum number of molecules have this much speed. Maximum number of the molecule have this much speed. Understood? So this is called Maxwell. This graph shows that at a particular temperature. So let's take it as a room temperature, or say 20 degrees Celsius. At 20 degrees Celsius, these are the ranges of the speeds they have. Similarly, kinetic energy is also like that. Kinetic energy also, there is 0 here, some number here. So these represent, that means this many number maximum particles are having this much energy. Okay, so this is Maxwell's distribution curve. Also, this is at a particular temperature, say 30 degrees Celsius. What happens if the temperature is decreased? Will the shape of the graph remains the same? If the temperature is decreased, what we notice that at lower temperatures, the peak will be, okay, I'll draw another graph. Say this is the number of molecules, this is speed. Okay, let this be at one particular temperature. This is at 20 degrees Celsius. Now, at say 5 degrees Celsius, the graph will be like this. What has happened? The peak has been shifted to the left, and the number of molecule is more. See, look here, this is more, but this is less. So this is at say 5 degrees Celsius at a lower temperature. Now what happens if you continue heating, if you draw a graph for higher temperature, say 40 degrees Celsius, for 40 degrees Celsius, the graph will be like this. All the shape remains the same, but what do we notice? The peak shifts to the right. Let this be 40 degrees Celsius. Okay, so what do we observe? Number one, as temperature increases, the peak shifts to the right. Understood? Number two, see, look here, the peak value, what happens? Peak value decreases. Okay, the number of molecules or the peak value, the maximum number of molecules, right, decreases. Peak or the maximum number of molecules decreases. Also, you can notice one thing. See, look here, all the graphs starts here. What does that mean? So this number is 0. There are no particles with 0 speed. There are no particles with 0 kinetic energy. What does that mean? That means all particles are always moving. No particles are still. Okay? There is no particles with 0 speed
Miss,
or
pull the paper up.
0 speed or energy. Okay, very, very important. This is Maxwell distribution curve, or when you go for high studies, they'll simply tell you Maxwell's distribution. That is nothing but a graph of number of particles having each speed or each energy. And as the temperature increases, two things you notice: the peaks shift to the right, but the peak value decreases, and this point. But you can say one more final point. But the area under the graph all remain equal. This area, and this area under the graph remain same. What does the area show you? The number of molecules. Area under the graph remains same. What does the area under the graph gives you? Total number of molecules. Distribution, okay, fine, yeah. Mark a vertical line on your graph to show the energy corresponding to most probable speed of the particle. Label this as C naught. From the Maxwell distribution statistics, most probable speed C naught, mean speed C, RMS speed C square are in the ratio this much. Mark two more vertical lines on your graph and label these. Okay. Okay, fine. That is this one. In this graph, which is the most probable speed, the most probable speed is this much. Okay. Where shall I write? This value. Okay. This value is the most probable speed C naught, according to your question. This value, most probable speed. This speed is the most probable speed. Now, which is the average speed? Average speed is slightly to the right. This value is average speed. Okay, or mean speed. This is the average speed or mean speed. Mean speed C we write. This is the mean speed. Now RMS speed is slightly to the right of that. So this C square, okay, RMS speed will be like this, square root of average speed. This will be RMS speed, this will be mean speed, this will be most probable speed.
Got it.
Okay, and they are in the ratio of 1:1.13 to 1.23. Okay, so they are to the right. So that also please note in your graph. Now, what would be represented by the area underneath the Maxwell-Boltzmann curve? Huh?
The total number of molecules.
Total number of molecules in the investigation. That's what I have given in the last point. Area and A, okay? Because number of molecules per speed into speed will give you speed will get cancelled, number of molecules. All right. Now, did you get the answer for that question that I gave you? The first one. I just want you to be familiar with the calculation. That's all. What answer you got? They give you a lot of questions based on half mc square is equal to 3/2 kT. It gives you what? You find out. Okay, what do you get? 18 plus 273. So 273 plus 18. 291. Okay. So 291 Kelvin. Now you have to find what? The RMS velocity. That means C square. Okay, you have to find this. What equation do we have? Half mc square is equal to 3 by 2 kb into T. This is the equation that we have. We have to find C square. Mass of helium we know. Value of this one you know. Temperature you know. So therefore, C square is equal to 2 and 2 goes 3 kb T by m. So 3 into, what is the value for kb? 1.38 times 10 to the power of negative
23.
23 kb, okay, into T, 291 divided by mass of helium. What is the mass of helium? What is helium made up of? 2 protons, 2 neutrons. So it is a 4 times proton and neutron are having similar mass, 4 times mass of a proton. Okay. So what is, so that's 4 into, what is the mass of a proton? 1U, 1.661 into 10 to the power of negative 27 kilogram. Okay. So this is C square. You have to find RMS speed. So RMS speed is square root of C square. This is what you want. Okay. Please learn to use this equation. $1,000. Okay. 1,000. Okay. Now I gave you another past paper question. Sanjita, understood? Fareen?
Yes, miss.
Okay. So now you do the second question. A mixture of helium and hydrogen gases is maintained at 300 Kelvin. Average kinetic energy of helium. Helium is EK. Their average speed is V. Which statement is correct? Again, based on this equation. This one, I gave you one multiple choice question in a group. A mixture of helium. Okay, you want, okay, you want to do that now. I thought you can do that as homework. Anyway, which molecules will have kinetic energy in the mixture of nitrogen and hydrogen molecules at the same temperature? Which molecule will have more kinetic energy at same temperature? So, same temperature, kinetic energy.
Same kinetic energy.
Same kinetic energy. So, okay, please understand. What is this? Kinetic energy is equal to 3 by 2 kb into T. This is a constant. Okay. So, at same temperature, same kinetic energy. But what is different? Half mc square. Okay, kinetic energy, this is same. But if a bigger molecule has, if mass is more, C square will be less. Okay. Yes, so that's what I made you right. That I made you right. At a particular temperature, all molecules, even if it's a mixture in a gas, they have same energy. How is that possible? One is big, other is small. Big travels slow, small travels faster. So now you answer this. Which molecule has same has more kinetic energy? Kinetic energy same. Hydrogen has same kinetic energy as helium if, what is the condition? If temperature is same. Okay. Now, even though they have same kinetic energy, hydrogen and helium, or here nitrogen and hydrogen. Next question. On an average, will hydrogen or nitrogen molecules be traveling fastest? Speed if you take. Speed if you take. Which has more speed, hydrogen or nitrogen? Hydrogen. Big molecules travel slow, small molecules travel faster. Okay. Please tell it to yourself this point. This point they ask you in the form of multiple choice, explanation questions, etc. Very important. Same temperature, same kinetic energy, but different speeds depending on masses. This much, okay. So now you do the multiple choice question which I gave you in the group. Similar concept. Yes, the average kinetic energy of helium is same as EK. Okay, all the other options are wrong. Now you do this question. Can you do this as homework? Do this question as homework. Calculate the increase in kinetic energy if the temperature of an ideal gas increases by 1 Kelvin. Increase.
Miss.
Hmm.
Miss, I have this question. Miss, is air an ideal gas?
What is air? Air is a mixture of real gases, right?
Yes, Miss.
There is ideal gas is only an imaginary gas, because no gas that we know behaves exactly according to ideal gas rules. All the gases that we know around are called real gases. They obey these gas laws for certain temperature, not for all temperatures and pressures. Ideal gases are supposed to be following gas laws at all possible temperatures. So there is no ideal gas actually in the universe.
Okay, Miss, there was this question actually if air is an ideal gas, but the answer was no because it has a finite volume. But then again, there was this question where the temperature was 20 degrees Celsius and they asked if air is an ideal gas. And there the answer was yes, air behaves as an ideal gas here.
No. Okay, remember I gave you a graph of an ideal gas and a real gas. They behave almost similar way when the temperature is less and pressure is high. Okay, I told you that one, right? When does a real gas behave like an ideal gas? When real gases behave like ideal gas at high temperature and low pressure. So this is a PV graph for that one. Only at when the pressure is too low and the temperature is high, real gases approximately behave like ideal gas.
Okay, Miss.
Okay.
Yes.
For example, I'll show you another graph in which another graph I'll show you. What is the ideal gas equation? PV is equal to nRT, or PV is equal to capital N kBT. Now, if you draw, okay, where R is the ideal gas constant, right? So what is R? R is equal to PV by N into T. So if you draw a graph between this R, and pressure, okay. So for ideal gas, this R is supposed to be constant. So this is the graph for ideal gas. Ideal gases have this universal, this constant R. This is what? PV by RT. Now, these real gases, okay, as the temperature decreases, this is the real gas at low temperature. If you increase the temperature, it will be something like this. If you further increase the temperature, this graph may be like this. So, real gases behave like ideal gas at high temperature and low pressure. Okay, there are many graphs that tries to explain all these things, but we don't have any gas in the universe obeying all the ideal gas concepts.
Okay.
Okay, the pressure exerted by an ideal gas. Then we have learned that the temperature is a measure of the kinetic theory, pressure, temperature. Now another variable, there are two more variables which you need to study, that is internal energy and thermal energy. Internal energy. What do you mean by internal energy? What is inside an object so that it can have internal energy? What is inside an object? Molecules. Molecules, right. So what all the energies these molecules have, that is the internal energy. Now, what are the molecule energies that these molecules have?
Kinetic energy.
Yes, very good. Why? Why kinetic energy?
Because they vibrate.
Molecules have number one, kinetic energy, because they are moving. Since the molecules are always in motion, they have kinetic energy. What other energy they have?
Potential energy.
Potential energy. Why they have potential energy? Because there is force of attraction between them. Okay, between molecules, there is force of attraction between molecules. So what is internal energy? Internal energy is represented in other books by the letter U. So I'm also going to use that. Don't use I, because I is used in too many places. Internal energy is the sum of kinetic and potential energies of the object. Can I write of the object?
Of the molecules.
Internal of the molecule. So this is microscopic property. Internal energy is called a microscopic property because it is dealing with the microscopic things inside an object, nothing but molecules. Okay, internal energy is a sum of kinetic and potential energies of the molecules or particles inside an object or in an object. Okay. Now, so this is actually what internal energy means. Now let's talk about internal energy of a real gas, internal energy of an ideal gas. Okay. Now, internal energy of a real gas. Internal energy of a real gas. Now check whether real gases have these two energies. Internal energy of a real gas. Real gases have number one, kinetic energy because the particles are moving. Number two, potential energy. Therefore, internal energy of real gas is equal to EP plus EK. Okay. Now, what is the formula for EK? Half MC square, which is equal to 3 by 2 kT. This EK is equal to what? EK, I'll write that over here. EK is half MC square, which is 3 by 2 kB into T. Now, potential energy is by van der Waals equation, which is a little complicated one. You don't need to study. Okay, van der Waals equation. So this much you study. That's enough. So you've got kinetic energy can be found by half MC square, which is 3 by 2 kB into T. Now, what about the internal energy of a internal energy of real gas? Use kinetic theory assumptions. Do they have real gases? No, ideal. No. Ideal gas. Ideal gases have number one. Do they have kinetic energy? Yes, but what is their potential energy? What is potential energy due to? What is potential energy due to? Force of attraction. Okay, potential energy is due to force of attraction. Do ideal gases have force of attraction between the molecules? Read through the assumptions.
No, miss.
No. Okay, this is zero. This is there. This is zero. Why? Because according to kinetic theory, no force of attraction between molecules. Okay, so the internal energy of an ideal gas is only due to its kinetic energy. So half MC square, and that can be found by 3 by 2 kB into T. Okay, understood? So the internal energy is due to the kinetic and potential. Why kinetic you understand? Because they are moving. Why potential you understand? There is force of attraction. Real gases have both of them, so they have some of these two. But ideal gases have no force of attraction. Therefore, only their internal energy is only due to a kinetic energy. Now, what is heat energy? Another term that we use is heat. Heat energy. Though you may think that heat energy, internal energy are all same, they are kind of same, but it's only a technical difference. For example, assume that this is a block. You are heating this block, maybe by a heater or somehow. As a result of this is what? Heat energy, H. As a result of you giving heat energy from outside, its internal energy U increases. The heat energy that you gave is causing an increase in the internal energy. So what happens to the molecules inside is internal energy. But how much energy is given from outside? From outside is heat energy. Or when you cool it, how much energy does it lose? That also is heat energy. So heat energy is basically from external, from outside. Outside, how much goes into, outside, how much comes out. Okay, how much comes out to outside. But internal energy means as a result of you giving or the energy leaving, what is the change happening inside? To you.
Yes, miss.
If there is no energy loss, this heat energy which you supply is fully utilized to cause an increase in internal energy. This is the relationship. If there is no energy loss, the heat which you give from outside, maybe by a fire, maybe by a heater, or maybe by light, or somehow, how much energy this object receives from outside, which is called its heat energy, that is converted, fully utilized for increasing the internal energy. Okay, so then what is heat energy? The amount of energy. Please write. That comes into or goes out of a system. The amount of energy that comes out or goes into a system when cooled or heated. There is a condition when, there is a condition if the heat energy causes change in temperature. And the relation with internal energy in the context of change in temperature, which means if you heat an object, will always temperature change? When you heat an object, will the temperature change all the time? This is the equation only if the temperature changes. Is there a different situation where you are giving heat energy but the temperature doesn't change? Will this happen like this?
Yes.
When? Yes. Answer is yes. When? When there is a change
in state.
Yes, change of state. Okay, you are heating, you are giving energy, but the temperature doesn't change during a change of state. For example, you can see that in a heating curve. What is a heating curve? Heating curve, assume that you have got, say, ice of 1 kilogram ice, okay, at say minus 10 degrees Celsius. You are heating this by placing it on a heater. There is a temperature inserted to know the change in the values of the temperature. Now, let's plot a graph of the temperature variation of this until it boils. Okay. Now, if you draw this graph, is very, very important. Tells so many things about this heat. Okay. So here, what do you have? Temperature against time. Now, assume initially this is at what temperature? Say minus 10 degrees Celsius. as you continue heating, as the heater continues to give energy, the temperature of this slowly rises until the temperature becomes 0 degrees Celsius. Okay, here the temperature. Okay, here the temperature the temperature rises. And then the temperature doesn't rise for a certain time. Temperature remains constant. And what is happening here, even though you are supplying energy? Here, melting happens. Melting is a change of state. Melting happens. Here, only the temperature is increasing. Here, melting happens. Then, when all the ice has turned to water, then the temperature rises again until the temperature becomes 100 degrees Celsius. Okay. Then again, the temperature doesn't rise. Even though you are continuously giving heat energy, temperature doesn't rise. Why the temperature doesn't rise? A change of state is happening, which is boiling. Okay, here melting is a change of state. During that change of state also, no increase in the temperature. Similarly, in the case of boiling. Now, when all the water has boiled to gas, what happens? Temperature rise again. Okay, so here temperature increases, here temperature increases, here temperature is a constant, here temperature increases. Okay, so now what we did earlier is when there is a change in temperature. So for all these slanting part, how do you calculate? E is equal to MC delta theta. This or PT is equal to MC delta theta. VIT is equal to MC delta theta. This can be used for 1, 3, and 5. 1, 3, and 5 to calculate the amount of energy absorbed for heating or the amount of energy given out during cooling. So this is a heating curve. Now you have to identify what is here, what is here, what is here, and what is here. What do you find over here? This is ice. This is the end of ice state, or yeah, this is the place where ice is beginning to become water. So here what do you have? Ice at 0 degrees Celsius. Ice at 0. Okay. Then what do you have here? Here all of them, all the ices turn to water. So water at 0 degrees Celsius. Now the temperature of water begins to increase until this one. Here what do you have? Water at 100 degrees Celsius. Then boiling. Then hello? 100 degrees Celsius. Here what do you have? Steam at 100 degrees Celsius. Then the steam increases. Now you have used E is equal to MC delta theta for this part, and this part. And for this part and this part, there is a change of state. For these two parts, how will you calculate the internal energy? Okay. So these two parts, you can calculate the energy by the equation E is equal to, for this part, M into LF. Where what is LF? Specific latent heat of fusion. Amount of energy needed to melt 1 gram of ice or 1 kg of ice at constant temperature. So this is a formula that you have to use for E is equal to MLF. PT is equal to MLF, VIT is equal to MLF. Similarly here, E is equal to M into LV, latent heat of vaporization. Generally, when you combine these, you can write E is equal to M into L, where L is the specific latent heat of fusion for melting, vaporization for this much. Okay, so if there's a change of state, use ML, change in temperature, MC delta theta to find the internal energy. Okay, and heat energy is by PT, VIT, all those formula. Very important graph. Please take it down now itself. So this is the end of thermodynamics. Okay, there's only one small experiment which I will explain later. Now you take it down. Next class there will be a test on thermodynamics. Okay.